Welcome to part 3 of stereochemistry. To this point, we've discussed how to establish if a molecule is chiral. Now we need to name each enantiomer of the pair. And chiral centers are designated as R, or rectus, or right, or S for sinister or left. And this is done by ranking each group around the stereocenter from 1 to 4. 1 being the highest priority, and 4 being the lowest priority. And the way that we assign priority is through what's known as the Kohn-Ingold-Prelog rules, which ranks groups based on their atomic number. Best way to learn how to assign a chiral center as R and S is just to do it. So let's zoom in. And we've used this example in the past. We've got 2-propanol. And it comes in 2 forms. Here's one where we're going to have the OH coming out at us. We'll call this compound 1. Or the other where the OH is going back, and we'll call this compound 2. And for this discussion, we're going to focus on compound 1. So we're going to follow the following rules to assign R and S. So rule 1 is to assign each atom attached to the chiral center a priority based on its atomic number. The group with the lowest priority, smallest atomic number, is given the number 4, and the highest priority, largest atomic number, is given the number 1. And we're talking about the atom that's directly attached to the chiral center. If 2 groups have the same atomic number, a priority cannot be determined. In these cases, we will move to the next atom to see if there's a point of difference and continue away from the chiral center. And this is important. We're moving away from the chiral center until a point of difference is found. And rule number 3 is once all the groups have been assigned a priority, the lowest priority group is directed away from the viewer. So we're going to arrange the molecule so our lowest priority group is away from the viewer and trace from the group with priority 1 to 2 to 3. And if that direction is clockwise, then we assign it R. If the direction is counterclockwise, then we assign it S. So let's go down here, and we're going to redraw compound 1. So here's compound 1. OH, H. Okay, so the first thing that we do is we need to look and find our chiral center. The way we find the chiral center is it's the carbon that has 4 different things attached to it. So this carbon is got 4 different things. We've got a CH2 and a CH3. Okay, we've got a CH3, so a methyl group, an OH, and an H. So this is our chiral center. At this point in time, what we need to do is we need to assign each group a priority based on its atomic number. So here we've got an oxygen directly attached to the carbon center, a hydrogen, a carbon, and a carbon. So right off the bat, what is our atom that has the highest atomic number that's directly attached? A carbon, an H, or an O? And the answer is it's the oxygen. So this would be priority 1. Our smallest group, in this case, we've got a hydrogen. Anytime you have a hydrogen, it is going to be the lowest priority. It is going to be priority 4. So now we got to figure out what's going on. We've got 2 carbon atoms here. So this is where it helps to actually add in the C's and what's attached to them. So in this case is the methyl, so there's 3 hydrogens. And here we've got 2 hydrogens. And here in the end, we've got 3 hydrogens. So we've got a carbon and a carbon. Well, what's attached directly to this carbon atom? Because we still have the point of difference. We haven't reached a point of difference because this is a carbon and that is a carbon. So what's directly attached to this carbon atom? Well, what's directly attached to this carbon atom is a hydrogen, and a hydrogen. So we mark that. We write that down. It's going to be H, H, H. what's directly attached to this carbon atom? Well, we've got a hydrogen and a hydrogen. So we've got an H and H. So far we haven't broken the tie. But unlike the methyl, right, it's attached to another carbon atom. So it's going to have a C. So, did we break the tie? Did we find a point of difference? Well, this is HHH. This one's HH, so it's tied up until we get to the third atom, which in this case is a carbon. So this one wins. So this carbon over here is going to be carbon 2, and this is going to be carbon number 3. So what we do now is, now that we've assigned our priority, or our priorities, we then trace from 1 to 2 to 3. Now the good news is my lowest priority group is going away from me, so we can just ignore it and trace from 1 to 2 to 3, and when we do that, we'll use green this time. 1, oops, let's erase that. So it's going to be 1 to 2 to 3. And which direction are we going? Well, in this case, we're going clockwise, right, around the clock. So this chiral center would be R. So this, right here, our chiral center is an R chiral center. Now, a common mistake that students typically do when they're new at this is that they do not orient their lowest priority group away from the viewer when determining R and S. And this is very important, okay? You must have your lowest priority group going away from you, because if your lowest priority group is coming out at you, what's going to happen is you are going to get the incorrect answer. You're going to get the opposite and incorrect answer. So, there are two ways to deal with this. One, you can redraw the molecule so that the lowest priority group is going away from you into the plane of the paper. Or the second is you can assign the rotation and then reverse the answer that you got. Let's do this. Let's show what I'm talking about here. So we're going to do this. Okay, so now this is going to be compound 2. So here's my OH. My hydrogen is coming out at me. So our oxygen is going to be 1. Our hydrogen is going to be 4. This carbon here is going to be 2. This carbon here is going to be 3. Now, what do we notice? We notice that our lowest priority group is coming out at us. Remember, assigning R and S, you need to have your lowest priority group going away from you into the plane of the paper. Right now, our highest priority group is actually going into the plane of the paper, okay? The big no-no is that we've got our lowest priority group coming out at us and not going away from us, okay? It needs to go away from the viewer to assign R and S. So if we assign R and S to this, as it is written, 1, 2, 3. Well, that's saying that in this case that this is also R. Well, that can't be the case, because this is compound 2. And compound 2 is the mirror image of compound 1, and they can't have the same designation, right? They're mirror images. If this one was R, this one has to be the other designation. This one has to be S. But the reason we're getting the incorrect answer is our lowest priority group is coming out at us instead of going away from us. So, in these cases, you can do one of two things. The first is that you can say that it's S because we just reverse what we get, or we could redraw this molecule. We could take this compound and flip it, redraw it like so, and then assign R and S. So if we flip it, what we're going to get is the following. Okay? OH, H. Now assign your priorities. This is priority 1. This is priority 4. 2, 3. We can ignore 4. So 1, 2, 3. We're going in that direction. So this would be S. So we get the same answer as if we just reversed it. So you can see that if for whatever reason our lowest priority group is not going away from you, you're going to get the wrong answer. You're going to get the opposite answer. So you can do one of two things. We can either reverse what we got, so we got R, reverse it, it's actually S, or we can redraw it so that our lowest priority group is going away from us, and then we get the correct answer. Again, in this case, it's S. So what if you have a double or triple bond bound to your chiral center? How do you treat those? Well, if you've got a double bond, you treat it as if that first atom of the double bond is bound to the second atom twice. So let's look at an example. So let's zoom in. So let's say we have this carbon atom, and it has a double bond to some atom Y. Here's where it's attached to the chiral center, and we have some R. So that R group can be a hydrogen, it can be another carbon atom, whatever. So what we're actually saying here is that this carbon atom of the double bond, or it could be any other atom, it doesn't have to be a carbon, but typically it's going to be a carbon, is really bound to this Y twice plus R. Because it's a double bond, right, we're saying that it's bound to Y 2 times. Y, carbon, Y double bond, Y, R. So, a specific example, let's say we had something that looks like this. We've got this carbon atom. Here's where it's attached to the chiral center here. So we're moving in this direction to try to find our point of difference. And we've got ourselves a hydrogen, and it's a carbon-carbon double bond. H. What this means then is that this carbon is bound to a hydrogen, a carbon, and a carbon. So if we redraw it, really what we're saying then is it's bound to this C. This carbon is bound to this carbon twice, so C, C, H, as such. So, what if we have a triple bond? Well, it's going to be the same thing. Now we've got a typically, again, it's going to be a carbon. Doesn't have to be, but it's going to be a carbon, something else triple bond. We treat that as if it were bound, that first atom of the triple bond is bound to the second atom 3 times. So if we've got something that looks like this, as a general example, here's our carbon. Let's say it's bound to some Y atom. Really, what this is the following. We're saying that this carbon is bound to Y 3 times, which makes sense because we have a triple bond. So this carbon is bound to Y once, twice, 3 times. So we'd abbreviate it this way: once, twice, 3 times. So in a specific example, we can look at an alkyne. Here we've got a carbon-carbon triple bond. Really, that's saying that this carbon is bound to the second carbon of the triple bond 3 times, because once, twice, 3 times. Here, this carbon, so we say it's bound once, twice, 3 times. And so that's how you deal with multiple bonds. There are some cases where you have to go to the second atom of a multiple bond to find a point of difference. In these cases, you actually look back. So if I had to go to the second atom, you look back from where you came from. We're not really going to have or get into too many complex examples. Typically, we'll be able to find that point of difference at that first atom of a multiple bond. Now that we've gone through how to assign RNS, how do we incorporate that RNS into the IUPAC name? So the rules for naming compounds that have chiral centers is the exact same. We're just going to add that additional R or S designation into that name. So let's do this by example. Here we've got a compound with a fluorine in it. We can see the chiral center. How do we know this is a chiral center? Well, I'm designating the stereochemistry by showing the wedges and the dash, but we can also look at it and say, are there 4 different things attached to this carbon atom? The answer is yes. We got an H, an F, a methyl, and then the rest of the molecule on this side. So let's name this compound. First thing that we do is that we number the longest chain. So in this case, we've got, if we start here, 1, 2, 3, 4, 5. So that's pentane, or 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. So we got 2 ways to get 5 total carbons, either starting from this side or starting from that side. Remember, we start from the side that has the first substituent on it. That means we're going to start here. So we start numbering here, 1, 2, 3, 4, 5. So it's pentane. We've got these 2 groups here, which are methyl groups, and a fluorine. All right, we got a fluorine here. So we've got 2 methyl groups. They're on the 3rd carbon. So it's a 3,3 dimethyl. And we got a fluorine on the 2nd carbon, so it's a 2 fluoro. And so now we put this together, we put this name together. So remember, in alphabetical order, so it's going to be a 2 fluoro, 3,3 dimethyl pentane. So there's the IUPAC name. Now we have to assign this stereocenter as R or S. So we look at our groups. Our lowest priority group is the hydrogen. It's 4. Our highest priority group is going to be the fluorine. It's 1. And now we have to look at each of these 2 carbon pieces, a carbon piece here and a carbon piece there. In this case, this carbon piece is a methyl group. So this carbon is attached to 3 H's. So this would be H, H, H. This carbon here is attached to 3 other carbons. Carbon, carbon, carbon. So it's a C, C, C. So this guy wins over here. So this would be 2. This would be 3. Our lowest priority group is going away from us, so we can ignore it and then count from 1 to 2 to 3. And when we do that, 1, 2, 3, we're going in a clockwise manner. So this would be an R stereocenter. And the way that we add this to the name is it's going to go out front in parentheses. So in this case, it's going to be R, 2-fluoro, 3,3-dimethyl pentane. We don't need to put the number designation on which carbon the R stereocenter is, because it's the only carbon atom that, this second carbon is the only carbon atom that actually has a stereocenter. If you were to put 2R out front, there's nothing wrong with that. It's just being redundant. But if you've got one stereocenter, you typically don't put the number out front. So let's do another example. Here we've got 1, 2, 3, 4, 5, 6 total carbons, right? We're going to start numbering actually from this side because our substituent is on this side. So, or our first substituent is on this side, so we're going to start numbering from there. So it's going to be a 1, 2, 3, 4, 5, 6. So it's going to be a hexane. Our substituents are a chlorine on the first carbon, so it'd be 1 chloro. And we have a bromine on the fourth carbon, so it'd be 4 bromo. Now we go to our chiral center. Again, it's easy to distinguish here because we are showing the three-dimensionality with the wedge and the dash. Again, if you had to check this, we've got to make sure we've got 4 different things attached to this carbon. And we do. We've got a bromine, a hydrogen, this whole piece of the molecule, plus a 2-carbon piece here. They're different, so it is a chiral center. So let's assign this chiral center. Well, our lowest priority group is our hydrogen. It's a 4. Our highest priority group is a bromine. It's 1. And now we have to distinguish or determine which side is higher priority. We've got a carbon and a carbon, so we have to try to break the tie. Well, this carbon here is attached to another carbon and 2 H's. So let's draw them in. So we got an H and an H. So this guy is a CH. This carbon here is attached to 2 hydrogens. So it is also a CH. So we didn't break the tie yet, so we got to continue on out. So we're still tied. We move to the next atom out. So we go to this atom, and I'll do this one in green. So let's start here. This atom is attached to 2 hydrogens and a carbon, so this would be a CH. This carbon here is attached to 3 hydrogens, so this would be an H, which means this guy over here, the point of difference is an extra carbon, so this one is this green carbon here on that I'm indicating with the pointer. That's going to be your second priority group. This would be 2. Oops. This would be 2. There's your 1. There's your 3, and again 4 is the hydrogen. So if we look at this, at first we're just going to go, okay, 1, 2, 3, we're going in a clockwise manner, but remember, our lowest priority group must be going away from us, and in this case, it's actually coming out at us. So we can either A, redraw the whole molecule, or B, we can just reverse whatever we got when we count from 1 to 2 to 3. And so if our initial count is going to be going in the clockwise manner, which would be R, but because our lowest priority group is coming out at us, we ignore that and reverse it, so it's actually going counterclockwise, so this would be an S stereocenter. And so when we name it, it's going to be parentheses S and parentheses dash 4 bromo 1 chloro hexane. So again, just remember, if your lowest priority group is not going away from you, you must absolutely reverse whatever answer you get, or redraw the molecule so that the lowest priority group is going away from you, because if it's not, when you assign R and S, you're going to get the wrong answer. So, just by using the R and S designation, it's a very straightforward way to determine if a pair of molecules are enantiomers. So, here are two examples, and we can determine if these two things are enantiomers by redrawing them so that we line them up so they look like they're mirror images, or we try to draw them so that they are lined up like mirror images, or we could just assign the stereocenter here, because mirror images are going to have opposite stereochemical designations. So if this guy is R, its mirror image then should be S. So the way that we can do that then is we can just assign each of the two stereocenters and see if they are the same or if they're opposite. If they're the same, they're the same compound. If they're opposite, they're enantiomers. So let's zoom in here. Our lowest priority group in this case is our hydrogen, it's 4. Our highest priority is bromine, it's 1. Here we've got a carbon, here we've got a carbon. So we have a tie, so we have to see what's attached to each of these. This carbon has 3 hydrogens. So it's an H, 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 right? There's 3 hydrogens, H, H, H. This carbon here, it's got 2 hydrogens attached to it plus an extra carbon. So this guy is going to be an H, H, C. Doesn't matter which way you put them in there. Our first point of difference is this carbon. So this piece over here is going to be our second priority. This will be our third. So we can ignore our fourth priority group, and we can keep in mind that it is going away from us, so whatever we designate this rotation will be the actual R or S designation. So 1, 2, 3, we're going in that direction. This stereocenter is R. Now let's take a look at this guy. Highest priority group is our bromine. It's going to be 1. Lowest is hydrogen. It's 4. Again, we've got the same pieces. This would be 3, or same pieces as this compound, because we're looking to see if they are enantiomers. This side would be a 2. Now we go 1, 2, 3. However, what do we notice? Our lowest priority group is coming out at us instead of going away. So that means we have to reverse whatever answer we get. So that's not the correct answer. If we reverse it, so the blue arrow, that gives us counterclockwise, which is S. So this stereocenter is S, this stereocenter is R. They are opposite of one another. So what this tells us is that these two compounds are in fact enantiomers. So using the R and S designation, it's a good way to figure out if two compounds are enantiomers or the same compound.